Hi Patreon. So this is the March video. The poll was interesting because the winner of the poll was Angela's Choice, which is just a lot of pressure. I didn't know if you meant that I should pick from the poll or if I could just talk about whatever I wanted. So what I ended up doing was scrolling back to previous suggestions and just looking for things I might be interested in. I saw a bunch of stuff about pulsars. I was like, oh. And then that kind of just turned into a main channel video. And I also keep seeing the one about capitalism and journals, which I think I also want to turn into a main channel video. It's a very interesting topic, but I have such strong opinions that I want to do some research first. I know a couple journal editors because I used to publish in journals, but now that I'm in industry, I publish in like industry journals, which are very different. But I want to ask them some questions before I just go making opinions on the internet. You know, that's probably a good plan. So instead, I thought I could talk about whatever I wanted. You would be surprised I don't really talk about physics that much in my day-to-day life. And what I've been talking about with people most recently is fast food. I used to work at McDonald's. I worked at McDonald's for like 9 years. Like I supported myself from age 15 to whenever I got my first job teaching high school with McDonald's. And so I have a lot of feelings, not about the food, but about the job and the products and the service they provide. And I saw this thing from Wendy's and I just but no one wants to hear my opinion on fast food. So instead, something I thought would be fun, let me know if this was fun or not. I pulled up an old lecture from when I taught this Search for Life in the Universe class in 2020, and I thought it would be like a fun, not really like ASMR, and not really like you know those YouTube videos where they're like, here's coffee shop noises, and you listen to it while you're working or whatever to simulate being in a coffee shop. This is a little simulation of being in a college course. So like pull out your notebook. We're going to do lecture 19. We're going to jump in and pretend we're nearly at the end of this class. And I'm totally going to remember to screen record. I'm going to do that right now. I wish I had 1, 2, 3 record. I wish I had that setup that like Twitch streamers have where like if I looked this way, I could see what you all are seeing on the screen, like with my face and the slides. Unfortunately, you're just going to see me looking this way a lot of the time, and I'm so sorry. I also want to say, before we get into our lecture about the discovery of exoplanets, that these slides were given to me by Meredith McGregor, who was a professor at CU Boulder when I was there, and I think now, I feel like she's at Johns Hopkins. I feel like she moved up somewhere. She is a brilliant astrophysicist. She does planetary disks, and this textbook, it's like Life, the Universe, and something else. She's now an author on like the 3rd or 4th edition, so she knows what she's talking about. She makes beautiful slides. I have edited them to fit how I want to structure this like little lecture, but I just wanted to say that because teachers sharing slides and stuff is so amazing, and I hope we continue doing that. And I also like the idea of being like, these were not made by me. So when you see the beautiful backgrounds and the beautiful colors, know that Meredith McGregor took a lot of time in PowerPoint to make sure everything looked nice, and I just went in and lightly edited it, just so you know. So today's lecture is going to be about exoplanets. What stars make good homes for exoplanets? How do we find exoplanet systems, and how do those systems compare to the one we know very well, the one that we live in? I actually do think I've talked about this on this channel before. You need stars to form with material around them that will form planets. The earliest stars in the universe were made of hydrogen and maybe a little bit of helium. And then, of course, they go through stellar evolution. They make carbon and all the good stuff and iron, nitrogen, everything. And they explode and they shoot that stuff into the galaxy. And then new stars form in clouds that contain those metals. Remember, in astronomy, everything outside of hydrogen and helium is metals. And those metals are what form planets. So if you want an exoplanet system, you need a relatively young star like the sun that can form around an area that has metals, because you need metals to make planets. The second thing you need to think about is stellar evolution itself. You need the stars to live long enough so that planets can form And then if you're thinking about life, which is the topic of this course, you need the planet to exist long enough for life to evolve on that planet. So we're talking not the bluest, brightest stars. There's this A through M. I have the little thing down here where this, I am not an astronomer. I'm a physicist. I have never memorized this. I don't know where it's from. I'm sure you could look it up. I've never memorized the OBA situation. I always just call them blue or red. That might not be great, but that's fine. So really blue stars, they're really massive. They burn through their fuel really quickly and then they die. So a blue star could live like 100,000 to like 1,000,000 years, whereas stars like our sun, it's going to live 10 billion years. So when you're thinking about which stars will be good exoplanet hosts, you need to think kind of like the sun, that will live long enough to allow things to happen. If your star has 12 planets around it, but it blows up and kills them all within 200,000 years, it's not really a great system to host life. The other thing to think about besides stellar evolution is stellar dynamics. So some stars are less stable than other stars. Really low mass stars will have periods of huge flares and then periods of like dimness. And that is not great if you're, trying to host planets and life and everything, because the heat output, the light output is going to be variable, which is going to be difficult to allow planets to thrive. A big solar flare can devastate a planet. This happened on Earth, the Carrington event. You might have heard of it. It wasn't a huge solar flare enough to like interact with our planet, but it did cause this huge issue with magnetic fields and it interrupted the technology of the time. And if that happened today, it would be pretty serious. But these really red stars, they can have really intense solar flares that will just prevent planets from having like a happy time. Finally, we need the environment of the star to allow for the planets to have circular orbits. The other option is an elliptical orbit, which is kind of like an oval. And that's a problem because what you're going to do is you're going to spend some time very, very close to your star, but most of your time very far away. So the temperature of your planet's not going to be very stable over its year. And that's a huge problem. So when you're thinking about what stars make good hosts for exoplanets, you think about the environment because you need metals to form planets. But you also think about the environment that you need nice circular orbits. You think about stellar evolution and where you need a nice stable star that's going to live a long time. And you think this might limit the population of exoplanets, but that's just not what we find. Once we figured out how to look for exoplanets, we found them absolutely everywhere. So what you're looking at, I feel like I've shown this exact plot on my channel before. What you're looking at is at the total number of exoplanet detections versus the year. So this is adding up over each year. And right away you notice that this is just exponential growth. As soon as we know how to look for exoplanets, we find them everywhere. Since the first exoplanets were discovered in the early 1990s, the number of known exoplanets has doubled approximately every 27 months, which is amazing. Exoplanet science is a huge field in astronomy right now. It gets like half the funding. Although if you are in graduate school or about to go to graduate school, that means you should avoid this field because it's going to drop off soon because things go in waves. But that's just my opinion. If you're really into exoplanets, by all means get into it. Okay, so how do we find exoplanets? There are two ways, directly and indirectly. So the indirect method is easier because, of course, planets are very, very small compared to stars. And also, stars give off so much light that they're much easier to see than planets, which they do give off radiation, but they're mostly like reflecting light. So we're going to talk about the two methods. One is the transit method and one is the radial velocity method, which I will go into much more detail about. And then, of course, direct observation means you're just taking a picture. Like you are directly imaging a planet. Again, it's very difficult because planets are much, much smaller than stars. And also, planets are usually located pretty close to stars. So their light overwhelms the light of the planet. So the first thing we're going to look at is the radial velocity method. I think so. This is what this is. Okay. So let me describe these plots to you. So on the left, what you're looking at is the sun here in the center and the orbit of Jupiter out here. Jupiter is very, very massive compared to all the other planets. Like, the mass of our solar system was equal to 1. The sun's mass would be 0.999, and Jupiter's mass would be 0.001. And you could kind of throw away everything else, and that would be a good enough approximation. But that small fraction of mass that Jupiter provides is enough to cause the sun to wobble in its orbit a little bit. So rather than the sun being here and Jupiter orbiting around it, the sun and Jupiter are in a system where they orbit a common center of mass. So it's a really, really small shift off the center of mass, but it's enough for us to observe. So what this little circle here is showing how the sun is doing this teeny tiny orbit. It's kind of wobbling around the new center of mass. And on the right here is data. So this yellow circle represents the size of the sun on this diagram. And these lines show how the sun is moving. It's a teeny, teeny, tiny wobble, but it's enough for us to observe. So if you imagine you have a star and then a Jupiter-sized exoplanet, what you can see is the star in your telescope wobbling a little bit over a year. And from that, you can indirectly infer that there is something pulling on it. Something is causing it to wobble, because otherwise it would just like be on its nice little orbit. So the way that you determine the wobble is with the Doppler effect. I'm sure you've all heard the Doppler effect, but when you're teaching a class and you say something like the Doppler effect, you have to go over it again. So let's just do it. You're gonna make me wee-woo. That's what I have to do. Okay. So the wobble in stars is observed with the Doppler effect in the emitted light of that star. We feel the Doppler effect most on Earth with sound waves, like an ambulance. So when a sound wave is moving towards you, it is shifted to a higher frequency, so the pitch goes up a little bit. When a sound is moving away from you, it's shifted the other way, so the pitch goes down a little bit. We observe this, of course, with ambulances. So like if you're standing still on a corner and you hear an ambulance, as it's coming towards you, it's like wee woo, wee woo, wee woo. And as it's going away, it's like wee woo, wee woo. That's what we observe. It's hard for me to do with my voice, but you know it. Just picture that in your head. That's the Doppler effect. Oh no, I wee-wooed before there was another example. Okay, so here's a train. If the train is stationary and it's like honking its horn, you don't hear the Doppler effect at all. When the train is moving towards you, the pitch of the honking goes up. When the train is moving away from you, the pitch of the honking goes down. The same thing happens to light, which you see in this diagram here. If a light is moving towards you, the frequency of the light goes up, it becomes blue shifted, it becomes more blue. If the light is moving away from you, it becomes red shifted. The frequency goes down, it becomes more red. You would not notice this if I had like a light bulb and I was doing this to you. You absolutely would not notice this. But with stars, which are super bright, and telescopes, which are high precision instruments, we can observe this in stars. So what we see is the sun moving towards us. We can see it be blue shifted, and then down here it's moving away from us. We can see it be red shifted. A teeny tiny wobble leads to a change in the emitted light, which we can observe. Well, no, that's not true. It doesn't change the emitted light. It changes how we observe the emitted light. There you go. And here's a lovely diagram explaining that exact same thing. So the radial velocity method of exoplanet detection relies on the Doppler effect. I'm going to go over this plot. Okay. I got to get serious. I'm going to sorry. Okay. So you have a star. It's this red guy right here. And orbiting that star, you have a massive planet, which is this blue guy right here. The planet is big enough that it causes the star to orbit a common center of mass, which is this little gray dot. The blue planet is not orbiting the star, it is orbiting the common center of mass, this gray dot. It's just gravity. So we're on Earth. we can't measure the planet. We can't see it. It's not as bright as the star. It's not giving off light. All we see is the star right here, and we take a look at its spectra, which looks like this. Okay. If we turn our telescope back to the star sometime later, now it's over here. We might not even notice that it's changed position because this wobble is so small. But when we take the spectra, we see that because it's moving away from us now at a different velocity than it was before, all of the spectra is now redshifted. Notice this line here. In the spectra, you have this red line. Now that this whole thing got redshifted, that line is no longer visible to us. It's moved. From this, we can measure the velocity of all the things in this system. So imagine you look at this system sometime later. Now the star is moving towards us. That means everything is going to be blue shifted. So if you look here, there was a little blue guy here when this wasn't moving towards us or away from us. Now the star is moving towards us. This whole thing is blue shifted. We can no longer see that line. This red line has moved into the less red area. That is how we measure the Doppler shift in stellar spectra. And from that, we can detect, oh, what's happening? Why are you updating? No. Okay. I don't remember what I was saying. So when we observe a Doppler shift, we can infer that something is pulling on that star and causing it to jiggle. That's how we know it's an orbiting planet. Of course, it could be something else. Like it could be a binary companion that's maybe a black hole that we can't see. That would be a much bigger mass though. This also allows us to detect the mass, which I'll get into much later. But let me show you what this looks like on a plot. So that Doppler shift allows us to detect the star's velocity with super high accuracy because we know what it looks like. We see the shift. We can calculate the little delta V's in the star's velocity, and that's what's being plotted here. So if there was no planet, this plot would just be a horizontal line along 0. But what you see is this periodic variation where that star is doing like a circular orbit like this. So it's moving towards us, it's moving away from us, it's moving towards us, just like that. This gives us so much information about that planet. So depending on how massive the planet is, the larger this vertical shift is going to be. A very, very massive planet will cause a bigger wobble, right? But also, the repetition of this pattern, like how long you go from crest to crest, will tell us the orbital period of the planet. So with the mass and the orbital period, as I'll go into in a little bit, we can get more information about the planet, like its density and its radius. But this method was used to discover the first planet orbiting around a sun-like star, which won the Nobel Prize in 2019. So the discovery was in 1995 of 51 Pegasi b. I remember now that I talked about this in my sexual harassment video because there's a guy who didn't get the Nobel Prize for this. I'm not going to talk about that again because, like, it's done. I'm never talking about it again. But I will say I absolutely hate these pictures. I hate this. We don't have a picture of 51 Pegasi b. That's a cartoon. Someone has drawn that. We don't know if it's stripy. We don't know if it has an atmosphere. We don't know if it has wind systems. We don't know that it's yellow. I feel like this is fake news. This is bad science communication because I think people think like 51 Pegasi b looks like this and we don't know what it looks like. I'm probably going to repeat this complaint like 55 times through this lecture and I'm so sorry. But I hope that I can impart a similar hate for you. Like, you will see these and you will be like, we don't know what it looks like though. This is a cartoon. Okay, so here is something we do know. We do know the mass and radius of 51 Pegasi b compared to Jupiter. So this planet is less massive than Jupiter, but it has a much bigger radius. We can also compare our stars, which we have imaged. We can image a star, that's fine. So 51 Pegasi is more massive and larger than our sun. So you saw the graph though, since 1995, we have 4,000 exoplanets. It's crazy, it's amazing. Let's do a quiz. So one thing I miss about teaching is if I was instead giving this as a lecture to students, I would ask a question like this and I would wait patiently for someone to answer, and we would have a discussion. Maybe we should live stream. No, live streaming is a bad idea. So instead, I'll read the question and I will pause so you can try to answer it. What are some drawbacks of the radial velocity method? A, the planet mass will be miscalculated if the orbital plane is tilted. So what that means is, like, you have your sun and you have the planet going around it. Some planets can be like orbiting like on a tilted, oh, that's not a good, like if the star is here, they're orbiting like this or like this or like this. And that's also going to affect our observation because we can only look from one angle. So if the planet's like this to us, we might not know because we see everything as flat. Does that affect my sound? I'm so sorry. B, it works for very massive planets, which are not as likely to host life. C, features on the stellar surface can affect measurements. Or D, all of the above. So, Jeopardy music. Which right? You guys probably learned in school the multiple choice test taking strategies where if all of the above is an option, that's usually the answer. So let's talk about these. Okay, so the problem with A is the tilting of the orbits. That is a problem, right? We only see from one viewing angle, and we're measuring moving towards Earth or away from Earth. So if the planet is on an orbit that's like at a tilted plane, we're only going to see it moving away and moving from. So we have to account for that in like the error bars of our measurement. Part B said that this works best for massive planets, which is true. The more massive your planet, the bigger the wobble. If you have an Earth-sized planet, the wobble is going to be very, very small and much harder to detect. So even though we have these really high precision instruments, smaller planets are just going to be lost in the error bars. Finally, stellar activity can affect these measurements. So I was talking about like solar flares and stuff. You can have large scale events in a star that will change the observations we see. So in order to confirm something like a planetary discovery, you need to take data over a year or take data for a few months and then come back 4 years later and take data again and be like, yes, the planet's still there. So it requires long-term measurements. You can't just get on your telescope for one night and confirm with the radial velocity method that a planet's there. Okay, so the second method of indirect detection is called the transit method, where there's a beautiful GIF here. I don't have to use my hands. So you have a star and a planet moves over it. We can observe a dip in brightness, right? Because the planet has cast a shadow on the star. So not all of the light that was reaching us is now reaching us. And we can use that with like high precision measurements to infer that a planet has blocked the light from the star, even though we cannot see the planet. We see this with Mercury and Venus in our own solar system when you can see the shadow go across the sun. Okay, so here is what that measurement looks like. You have a star and you are just focused on that in your camera, in your telescope, and you are just measuring like the amount of light you can catch from it. And as the planet moves across, you just measure the dip in light, which looks like this. So when the planet is over here, you have this constant brightness from your star. And then as the planet starts to, it's like ingress across the star, you see a dip in brightness and it reaches some bottom level. And then the planet will finish its transit. It will egress away from the star and our amount of light goes back up to its like standard level. From this, you can tell that a planet has crossed across that star. So this data can also tell us a lot about planets. So if the star is doing this like every 6 days, you will see a curve that's like flatline, flatline, exact same curve, flatline, flatline, every 6 days. That tells you the period of the planet. And then the dip in this curve tells us the mass of that planet. Well, tells us the radius of that planet, because the bigger the planet, the more light will be blocked, the bigger this dip will be. So small planets will do something like this, big planets will do something like this. And again, this is an indirect method to infer that a planet exists, which is really cool. This has been the most successful method just because it's pretty easy. And also NASA and ESA, European Space Administration, ESA, have made a couple telescopes, Kepler and TESS, to just do surveys of all stars. So these guys just took data constantly, and then users would download the data and be like, oh, we've observed something. And this method is also really easy for smaller ground-based telescopes. So this is data I took when I was in graduate school at the University of Kentucky. There was a rooftop observatory here. And what you do is you find some field stars in the background, and you measure the brightness from those stars, and then you find your star where you expect an exoplanet to be, and you just measure that little dip. And you've confirmed the exoplanet transit. So this is kind of, I imagine if you know any single person who has gone to undergrad for astronomy in the last 20 years, they would have taken data like this, because it's so easy to do with a pretty small telescope, and there's so much data, there's so many planets that need to be confirmed. So like Kepler will be like, this maybe might be a planet, and then amateur astronomers or undergrads will be like, haha, I will go check this. And you submit your data and you say, I've confirmed this exoplanet, and it's pretty cool. So what I did, I was like a grad student just helping undergrads take this data. It's kind of fun. We've done it. Exoplanet transits. Okay. So we did the two indirect methods. You have the radial velocity method, where you have to get really high precision velocity measurements. You have this method where you get just the change in brightness. It tells you information about the planet. And then, of course, you have the direct imaging of exoplanets. And in order to do that, you need to make a device to attach to your telescope to block the light from the star. I like this little image of someone just like holding a circle. So you block the light from the star, and now you can directly observe the little planet guys. This is real data. Okay. I've actually used something like this at that same telescope before, but we did it to look at Jupiter's moons. So you just get a big like sheet of a thing and you stick it on your telescope so you can better see the moons without them being like overexposed. I'm not a professional astronomer. Overexposed by the light from Jupiter. But let's look at some direct imaging of planets. Okay, now this is why I get so mad when they shove up that like yellow Jupiter and they're like, this is an exoplanet, because this image right here is the best image we've ever gotten of an exoplanet. This is from 2020. I'm sure we have like better images, but they still look like little dots. Okay. So you've blocked the star, and what you're seeing is 1, 2, 3, 4 planets in this system that are orbiting around the star. That's really cool. On this example, you see the planet and it will cross the star and come over here, which means that we've also confirmed the evidence of this planet using the transit method. So you can use both to look at this planet and get more information about it. And I want to pause here and say that this is an amazing feat of engineering. Like, we've done it. Pictures of exoplanets. It's amazing. Meredith, who gave me these slides, she works in planetary disks, so like the formation of baby planets from like dust and gas. And she also does amazing work imaging those, if you ever want to look her up. Okay. So here are some more images of that B Pictoris, the one that crosses the star. So you can see this is like a long term. You can't just take one image and be like, we've done the planet. So this is data from 2014 all the way to 2018. But that is an exoplanet. That's amazing, right? I'm really worried I'm staring this way the whole time. I'm so sorry. Okay. So to recap, we have these 3 methods. You can look at transiting exoplanets. You can take direct images sometimes, and you can take radial velocities to determine the wobble. All of these have strengths. For example, the transit method is really easy for smaller telescopes to do. You can measure a transit in usually one night, right? And yeah, you can't get the period of it, but your data can be added to like the catalog of data, and that's amazing. It works best for bigger planets though. Smaller planets are going to have a smaller little shadow. It's harder to do. The same thing with the radial velocity method. You need a lot of data over a long time, and it also works best for really, really large planets. With the direct imaging, it also matters where the planets are situated, because if you cover the star and you have a really closely orbiting planet, you're just going to lose it completely. So it works better for planets that are very massive, massive enough for us to see, but also far enough away from their star. Like we're talking like Uranus orbit level, so that we can observe. That's how you do it. Let's look at some of the data for the ones we have. Here it is. I've already said that all of these are sensitive to large planets. So this is a plot of the period, so the orbital period in days of the exoplanets versus the mass of those planets in units of Earth mass. And you can see, here's the Earth. All of the methods we have for observing exoplanets are sensitive to large masses, which means all of the exoplanets we have observed are like mostly very massive. We have some smaller guys, but most of them are supermassive. And it's not because Earth-like planets don't exist. It's just because we can't observe them yet. You can also see that a lot of the orbital periods are down here. That's because all of our methods for detecting exoplanets, it's much easier if the orbital period is regular and short enough that we can see a change. Do you know what I mean? Imagine you have a star and the exoplanet's like super far away. So it's on top of the star for like months and months. If you're doing the transit method, all you'll see is while the planet's here is like a constant peak. So if it's there for 3 months, you're not going to observe the shift when it eventually moves off. That's why you see all these guys over here. It's not because those types of planets are favored that we know of. We don't know yet. It's just that we can't observe these yet. It's just harder to find them. You might also notice this region here. Here's our Earth-like planets, but we also have our Saturns and our Uranuses. Where are those guys? Why don't we find these really big orbits? Because Saturn's really bright. It's really massive. Shouldn't we observe things like that? And it's for a similar reason. It's just the further the planet is from the star, the smaller the effect on the star will be, the harder it is to observe. Planets can be very bright, but they're not going to be nearly as bright as a star. And we're looking from very far away, you know? So when you see a graph like this, you have to remember experimental biases. Like, it's not that these guys don't exist, it's that we can't observe them. But it's also not that we don't want to observe them. We really, really do. It's just with our current methods, with our current equipment, it is impossible. Everyone keeps saying this will change with JWST, but I haven't seen it yet. JWST is still pretty young though, so maybe we're a couple years away from seeing more stuff. Okay, so how can we learn about the planets from this data? The exoplanets, not our own planets. Okay, so the transit and the radial velocity methods give us the orbital period of the planet. With the radial velocity method, we get the mass of the planet, because that dip in the change in velocity tells us the mass of the planet, because a more massive planet has a bigger wobble. I'm just going to go back so I can say that again. I'm so sorry. Okay. Oh, it's very far back. There it is. Okay. So this is what we get from the radial velocity method. The more massive the planet, the bigger this dip will be. So a tiny planet will do that. A big boy will do that. So we can directly get information, indirectly get information about the mass. Whereas the transit method gives us information about the radius, because the length of time right here, the length of time it takes to get to this valley versus this peak tells us how long the planet spent crossing the edge of the star. That tells us the radius. And from those two things, we can get planet properties. From the radial velocity method, you get the velocity of the planet, and using one of Kepler's law, you can get the mass of the planet. So you observe the wobble of the star, you get the planet's period and the planet's mass. So from the transit method, as I said, you get the radius of the planet. And you also get the period by looking at how often that repeats. Here's a nice little diagram of a few different exoplanets, and they put the radius of the planet on top so you can see its effect on this curve. So teeny tiny boys make a teeny tiny dip, whereas much bigger planets do that. Great. So these different methods give us mass, period, and radius of a planet, we can use that to calculate an average density for the planet. And I know, that doesn't seem very helpful. Like, if you have, for example, the average density of the Earth, that doesn't really tell you that there's oceans and an atmosphere. Do you know what I mean? But that kind of information is kind of all we have right now. We have an average density. But think about it. We have the average density of 4,000 exoplanets that are so far outside of our solar system that we can never hope to travel to them. It's amazing. It's amazing that we've learned that. So from density, we can learn a little bit about the composition of an exoplanet. So for example, here is Earth. If we took those same values and measured the average density of Earth, and you can see Venus really similar to Earth, but what you see is when you plot the exoplanets, you get this kind of nice curve. And you can learn, for example, if the density of a planet is very, very low, it's going to be a gas planet. If the density is very, very high, it's not going to be able to exist because it's going to be the density of like a neutron star or something. So you get this sweet little Goldilocks zone where you're like, okay, we need to have a rocky surface, and then we need it to be a little bit less dense than that, so we can also hope that there's an atmosphere and maybe liquid water. You don't want all water. You want some rock and some water. And that's the best we can do right now. But that's really exciting. So now I just want to briefly complain about something else and how this information is usually communicated to the public. Because if you care about science at all, you may have seen articles recently where they talk about like habitable exoplanet found, 17 habitable exoplanets found, and habitable is not a word with a strict scientific definition. Because like if you look at this plot, like Venus is habitable too, right? But could we live on Venus? No. What do you mean when you say habitable? So if you see a scientist saying that they've discovered habitable exoplanets, you should know that that's probably whoever owns that website or that journal trying to get more clicks, or the scientists themselves is self-promoting. Because what does habitable mean in this case? Like, okay, we have TRAPPIST 1F. It's right there. What does that mean? We have its average density, but that's all. That's all we have right now. Do you know what I mean? So what we can actually compare are the setups of the solar system. Like, how close are the planets? What are the orbital periods? How circular are the orbits? And we can also compare, like, what is the average mass of a planet? What is the average density to what it is in our solar system? And that's pretty interesting because our solar system is just so nice and perfect and regular. So you have the sun, you have the inner planets that have shorter orbital periods. They're much smaller, they're rocky, they're metal. And then you have these outer guys with much bigger, nearly circular orbits for all. And these guys are more gaseous, they're icy, they're very large, they have big radii. So first let's talk about the orbits. All of the planets in our solar system, Pluto's not a planet anymore, are on orbits that are so nearly circular that we call them circular orbits. But when you plot the orbital eccentricities, so eccentricity is a word that means how elliptical something is. So a circular orbit has an eccentricity of 0. An elliptical, like oval, very, very, has an eccentricity of like 1. It's like a hyperbolic orbit. Okay, here's the plot. So this is the average orbital distance. So for all the exoplanets, Earth is here at 1. We consider 1 AU like the standard. And then you have orbital eccentricity, which goes from 0, which is circular, to 1, which is like a hyperbolic orbit. It'll be kicked out of the system. And what do you notice? Like, look at this. There's a huge spread, but also a huge percentage of planets are on very eccentric orbits compared to our solar system. Like, here's Mars, Venus, Earth, Jupiter, Uranus, Neptune. Mercury's a weird boy. Mercury's the weird boy in the solar system. I think I've mentioned this before too. Like, when you model the long-term dynamics of the solar system, Mercury gets ejected like 2% of the time. Okay, so if we put a line here and we say like, okay, these are like very low eccentricities. This is where Mercury is. It's a pretty circular orbit. A large percentage of exoplanets have pretty eccentric orbits when you compare it to our solar system, but that's not unheard of in our solar system. For example, we have comets that are on really eccentric regular orbits, and they're stable. They don't get kicked out. Everything's fine with that. So this is our solar system, and it's very circular orbits compared to this exoplanet in red. And Phaethon, I don't know if that's how you pronounce it, is a comet in our solar system. It goes real close to the sun. Okay, the problem with this, if you're thinking about habitability and if these planets could host life, from Kepler's laws, you know that the time that it takes this planet to orbit like this little section is the same as the time it takes to do this whole guy. That means out here, this exoplanet is going to be very slow, and when it's down here, it's just going to fly right by really quickly. So you would have to have a planet that can control its temperature in such a way that when it's over here for like 90% of its year, it's warm enough and it's shielded from the heat for like the 1 month of the year where it's right by the sun, because it's going to be real hot and then real cold. And most of the time it will be cold. So when we're thinking about habitability, we tend to throw these out and say, if your orbit is too eccentric, you can't regulate temperature on your planet enough. Something else to notice, if we again highlight Mercury's position, but this time here it is on the x-axis, we find a lot of exoplanets are much closer, are much closer to their sun than our planets are found. So we think of Mercury as being very hot, it's very close to the sun, but we find planetary systems that have really short orbits, very, very close to their star. And of course, the way we find exoplanets prefers to find those. Those are easier to find than planets that are much further out, right? But it's interesting that we find them, but we don't have anything like that in our solar system. So those guys are up here. These are called hot Jupiters. So they're massive, massive boys like Jupiter that are very, very close to their star, way inside Mercury's orbit. Here's what that looks like. Okay, so first look at this bottom plot. This is our solar system. Here's the sun, like there's no image there of the sun. And then Mercury's orbit's way out here, okay? This is the TRAPPIST system. So if you zoom in, you will see that sun and then like 7, is that 7, 2, 4? Yeah, 7. I thought it was 7. 7 Jupiter-like planets super close to their star, way inside the orbit of Mercury. And they're all on these nice little orbits, very close together, super packed together. These are called hot Jupiters. And this is kind of interesting because when you start thinking about solar systems, before you can observe them, you might think that ours is the standard. And maybe you can't get close enough to your sun because like the solar wind has got to be huge. It's got to be quite hot. But this is a stable system that we observe. We find these hot Jupiters just very packed together, very close to their stars. Something else we find that's not like our solar system is planets that are orbiting in binary star systems. So stars like our sun are not that common. A lot of stars are in binary or tertiary. Is that tertiary? That's the right word. 3 stars systems. I always think of Tatooine, right? You have Luke walking across the desert and the 2 suns come up. Another question. So what type of orbits and binary systems allow for habitable planets, which means stable orbits? So a binary system is 2 stars that are in a system, they're born together, they're the same age, and they often orbit a common center of mass, so like they might do that type of thing. They can also be very far apart. So here's the question. What type of orbits and binary systems allow for habitable planets? Planets orbiting halfway between the 2 stars. So if you have your 2 stars and one's traveling through. Planets with circular orbits far outside both stars. So imagine you have your 2 stars real close together and the planet's like way out here. A figure 8 orbit around both stars. So that's like this. I don't know if you can see that at all. And then D, no binary stars host stable orbits, which I already said it was possible. So it's not D. Okay, the answer is B. So if your planet is so far outside the 2 stars, it will behave as if it's just orbiting around one massive star, and that's totally fine. But let's take a closer look at this. So you have these stars real close together. This guy is just going to think that there's one massive star there. And this can be a nice stable orbit as long as these guys also have a stable orbit. You could also have something like this, where it's a wide binary, the stars are pretty far apart, and then you have one of those like hot Jupiters, real close to the planet. It's not going to see this guy that much, so this could be a nice stable orbit. But something like this is just, it's not stable. You can't have something traveling through. It would get kicked out of the system, or it would even get kicked into one of these stars. This orbit just wouldn't last long enough to form a planet. And here's an example of, again, this is a cartoon drawing of a system where you have, this is a real picture of the stars, and then they've drawn the orbits of the planets on top. You have your close and binary, and then you have 3 planets that just orbit them both. And that is a common-ish type of system we observe. It's very different from our solar system because we only have one sun, but that doesn't mean it's not allowed. So this is Kepler 47, A, B, and C. I love the way they name planets. It's really cute. How does the solar system compare to the exoplanets we've observed? First, we find that a lot of exoplanets can be happy with orbits that are much closer to the sun than what we observe in our solar system. So you have hot Jupiters that are super massive and just hanging out very close to their sun. We also see that when compared to the solar system, a lot of exoplanets can have high orbital eccentricities that are not even close to what we see in our solar system, which is pretty much nice circular orbits. Also, we find that planets can be much closer together than what we observe in our solar system. Things can be tightly packed and also much closer to their star. And then finally, while we only have one star, that's not the standard model of a solar system. You can have exoplanets around binary stars, and they can be in stable, happy orbits, which means if you're thinking habitability, you might be able to find life around a binary star system. Okay, so now let's compare our solar system to the exoplanets we've observed in a different way. We have diameter, comparing it to the Earth, where the Earth is 1, versus planetary mass, again where the Earth is 1, so here 1 is the Earth, and all the orange dots are our solar system. So you have Mars, Venus, Earth, Neptune, Uranus, Saturn, Jupiter. What do you see on this plot? The first thing is here. This is one radius, and where Saturn and Jupiter are, and you can see, even though this is all one radius, there's a wide spread in allowed masses. So there's a large range of masses that are allowed for planets, even though they have the same radius. Where we see this like curve that goes up for our solar system, that's not necessarily how it is, because all of these planets have very similar radii, but widely different masses. The second thing you might notice is this area here. So here's Earth, and here's Neptune. What's all this? There's a ton of planets here between these 2 radii. But we don't see that. We don't have an analog for that in our solar system. In our solar system, the way you're taught it, the way you probably learned it in 4th grade, is like you have small rocky planets and big gas giants. What we observe is that that's not a cut, because if that was true everywhere, we would not see these. We observe something in the middle, a sub-Neptune, a super Earth that we don't have in our solar system. And there are a bunch. There are so many of these, and I'm so sorry. Here's some pretend pictures. So the only piece of information you should actually take away from this is the Earth, and these are some exoplanets we've observed with similar densities, but larger masses and larger radii. So they could be Earth analogs, or they could be more like Neptune, and we don't know. But the thing about these is, these are the most common type of planet. The most common type of planet we observe is one that we don't have an example of in our solar system, which just opens so many questions. The average planet is something we don't know anything about. Amazing. So this is the most common type of planet. Again, there could be some bias there because we are limited in what we can observe. We can't observe these tiny guys yet, so maybe it's not actually the most common type. But of the planets we've observed, the most common type is a super Earth / mini Neptune. This is just talking about how we don't really know what it could be. So it could be like a huge rocky core, or it could be a tiny core with a huge gas envelope. We have to get more data. And this is, of course, one of the things they keep talking about with JWST. The idea is that we could eventually take spectra of the atmosphere of exoplanets, which would just be amazing. It would be the biggest news of the year that year once that happens. So if you could take spectra, you could determine, like, okay, is this an Earth-like planet like this that maybe we could live on, or is it just a different type of gas planet? Not that we could live on it. We can't travel space. That's a huge problem. Okay, so we find a huge range of exoplanets, but the most common type is so interesting because we don't have something like that in our solar system to compare it to. So there are just so many open questions about these super Earths / sub-Neptunes. I kind of like sub-Neptune better. Super Earth, again, it just evokes habitability in a way that we don't really understand. It's fine though. It's totally fine. It doesn't matter. Another thing we've learned from Kepler is that stars all have planets. I do think people thought this. If you look back at like the old discussions about the Drake equation, he was always like, every star has at least one planet, probably. And that's true. According to the data we have, planets are incredibly statistically likely. Planetary systems are incredibly statistically likely. Almost all stars have one planet. Most stars have a system of planets. Planets are incredibly common. Our solar system is not that common, right? We have these planets that are segregated by mass and composition. They're all on nice little circular orbits. We have the wonderful Jupiter shielding us from asteroids and everything. This isn't really what we see, right? We see eccentric orbits. We see those really close orbiting hot Jupiters. We see super Neptunes. Nope, sub-Neptunes. We don't see that in our solar system. So we're in a special little boy. That's exciting. The fact that we don't observe solar systems like our own is not that they don't exist. It's that we can't observe them yet. We don't have the technological capability of finding these tiny planets. They could totally be there. Maybe an Earth-like planet is the most common type of planet, but we just can't observe them. And it's not because we don't want to. It's not because we're not looking. It's because we can't see them yet. It's a biases that we have to correct for by coming up with new equipment and better precision and all that good stuff. Okay, so now we have to talk about habitability, which I understand is very interesting, but it's also, it's a hard topic. I talked a lot about this in my Silicon Aliens video, but let's try to get, oh my gosh, I've been recording for an hour. See, this class is supposed to be an hour long. I'm so sorry. Okay, yeah, I'm probably going to cut a lot. You probably haven't seen an hour, so it's fine. So what do we consider when we talk about habitability? It's like how life could form. You need to be within the habitable zone. You need to have a planet that is close enough to the star to get a nice temperature, like an environment that will host life. You need a planet that is large enough to retain a atmosphere. You also need like a rocky core to control the temperature of your planet and pull in an atmosphere, and hopefully it's rotating and you have a nice little magnetic field for protection. I've already said atmosphere. You need liquid water and you need a magnetic field. Okay, great. So if you're looking at this and you want to talk about habitability, you can rule out planets that are smaller than Mars because you need that mass to host an atmosphere and stuff. You can rule out those high eccentricities. Like I said, they're going to spend most of their time very far from their star, which means they'll be very cold. And when they come back, they're going to get real hot. You can't have, like, I mean, maybe there's some sort of bacteria you could have, but when people talk about habitability, I really think they're implying, like, could a human be plopped on that planet and stay alive? So you limit the mass, you limit to circular orbits, and then you can limit to composition that you expect to be rocky, and you get this little 24 here. 24 out of 4,200 that might be habitable, whatever that definition is for humans, which is not zero. That's not bad, right? And we find planets everywhere, and 24 out of 4,200 it's pretty good. It's a pretty solid chance, but it's not like we could ever get there. We can't travel space. We don't know a lot about these sub-Neptunes or super Earths. So when we think of like what's the perfect Goldilocks zone for a planet to be in, we're always thinking about Earth. That will change if you have a more massive planet with a bigger atmosphere. So you can kind of extend the region of possibly habitable to these super Earths, which is one of the reasons people are so interested in studying them. And again, here's a list of possibly habitable planets with cartoon drawings of what they might look like. Very silly. Okay. This plot's very funny to me because they ranked them by how close they are, as if 4 light years is any different from 1100 light years. Like, those are both impossible, but I hate to be a downer. Okay, so if we had actually done this whole class, I would have already done a couple lectures on the different types of habitable planets. Like, it's not just Earth. There are also these ice worlds like Europa that should have liquid ice oceans. They should have ice, or not ice, they should have like water lava vents where it's hot and it's stable and life could form there. So you kind of have to open your habitability if you're just looking for life, right? So considering like an icy planet like this, it really increases like the fraction of possibly habitable planets. And I think there's one more type of planet. Yes. So there's also rogue planets. So if every solar system forms like 9 planets, and some of those orbits end up not being stable, or if there's a weird interaction between the multiple stars or the different planets bouncing around, you can get planets that get kicked out of their solar system. So they will be kicked out of their solar system, but they might not. So kicked out of your solar system, you could be like flung into your star, or you could just be flung into the galaxy. And these are called rogue planets. They haven't been observed, but it's one of those things that must exist. Statistically, planets are so common. Computer simulations show this happening to things like Mercury a huge percentage of the time. These must exist. And so the idea is like, could life exist on these rogue planets? And maybe, for a while, if they have internal heat and they're massive enough to maintain an atmosphere, you could have, however long the energy exists on that planet, life form on those planets. It does remind me of that Twilight Zone episode where the Earth just gets kicked out of the solar system. Do you remember that? That's a good one. Okay. Oh yeah, here we go. So this is the end of the talk where it's like, well, we don't know. We don't know anything about the habitability of planets, but maybe JWST, and I gave this talk 3.5 years ago, and I have not seen anything out of JWST yet. But I will let you guys know if I ever come across a paper where they actually are doing spectral analysis of an exoplanet atmosphere, because I would be so excited. Okay, here's the takeaways. You need a specific type of star to be a good host to an exoplanet, but you also need a specific type of exoplanet. It has to have a nice orbit. It has to have a nice mass if you're considering habitability. We have found so many planets through so many different methods, and it's amazing. What a time to be alive. That's the takeaway. Okay, so if this was a real class, next we would be talking about galactic position, because there's a Goldilocks zone in a solar system to allow for habitable planets, but there's also a Goldilocks zone in the galaxy. We can talk about the rarity of Earth by looking at the Drake equation. And because this was a search for life in the universe class, we ended up talking a little bit about measuring intelligence and what it would be like to find an alien versus intelligent species. But this was a fake class, so that's it. I don't know what you expected when you picked Angela's Choice, but this was Angela's Choice. Exoplanets. I like exoplanets. Okay, so I got 100 new patrons last month. So hi, new patrons. I usually end by talking about the last Patreon video, just if there was any confusion or if there were any comments. And in the comments of that video, 6 people recommended this book, so I bought it. I don't ever buy books new, but so many people recommended it that I purchased it. I'm really excited to read it. I am on a journey this year to read classic sci-fi, so this just fits right in. I'm a little worried because I think it's the first in a series, and for some reason I'm just on standalones recently, but I am excited to start this. So yeah, apocalypse physics. Oh, also, I was just in Vegas. I went on vacation. I mentioned this on Patreon. It was like my first vacation. I thought it was 10 years, but I went on vacation in 2016, so it wasn't 10 years, but it was close. I went to the Atomic History Museum, and I thought of you guys because I'm going to take a picture. I saw this experiment. So they had the device and then the stack, which is what you're looking at from this experiment in the 90s. And in that apocalypse physics video, I talked a lot about how one person can't do physics. It's just impossible now. And this is kind of what I mean. Like, if I walked into a lab, there would be 6 of these. And even if I could look at it and I could say, okay, this is an amplifier, I would have to see 700 cords and be like, why is this attached in the circuit here? What is this doing? And then you look 4 down and it's a different amplifier set at a different level and a different location. And it would just take, like, even if I understood the theory of the experiment, like what the experiment was doing, actually physically with my hands figuring out what was happening would be impossible. And that's why people go to grad school for like 7 years and they work in labs and they learn how to do an experiment from the ground up. It's a very complicated process. It requires a lot of people working together. This is amazing about physics, but that also means you can't really do it by yourself. So I was there and I saw this and I was like, this is exactly what I was talking about. So I had to tell you guys. Here you go, guys. There it is. That's an experiment. That's kind of what a modern experiment looks like. And actually, these racks and this equipment, it's still in use today. Like, you could take that out and put in a brand new one and it would be very similar and they all work together. And this is also why there's like a little bit of superstition in experimental physics. Like, you walk in and you're like, okay, so that wire has to be on the floor because if we set it on the table, it stops working for some reason. And I think that's great and fun. So the next thing in these Patreon videos is I just talk about what I'm working on next. So last time I talked about how I was going to do a video on the Nobel Prize, and I did not. I wrote the scripts, and I just didn't, I don't know. It's not that it was bad, I don't think anyone who watches my channel would want to watch it. So I don't know, maybe I'll record it, I'll put it up here as a bonus video, and you guys could tell me if I should just publish it or not. Maybe I'll do that. But I thought it was interesting. I don't know, I'm kind of in my head about what the people who watch my channel want to see versus what I want to make. I can see why some really famous YouTubers, like, I'm nowhere near like a famous professional YouTuber, but you know how they take like a year to do a video and then like it's another full year. I feel like I really understand that because I get to a point where I'm like, okay, it's done, I should record this, and then I'm like, oh, but I could research something else, and I don't know. But maybe I'll record the Nobel Prize video. I will post it here and you guys can let me know. For my main channel though, I am working on a lot of like big projects that require a lot of reading. Right now I'm doing the temperature video. Someone on Patreon recommended me this. It's kind of interesting. I think I'm gonna approach it from like Planck's view of temperature. So that should be the next one. Okay, and the last thing I want to tell you guys is that I've been talking to DFTBA, the Green Brothers merch website, and I'm going to make a t-shirt. It's just going to say, it's fine, I think. I think that's going to happen. We now have like a design. So I think maybe in another 5 months there will be a t-shirt. And they said, I mean, first of all, don't feel obligated to buy anything. It's totally fine. It's totally fine. But they did say I could give you guys a discount code. So whenever that launches, if it launches, I will give you a discount. If you stop being a patron before that comes out, just send me a message on Patreon and I'll give you the discount code. If you've ever been a patron, it's fine. It's kind of nice. Like, it's like a real, like, when all this is over and when I'm done being a YouTuber, I can be like, no, it was a real thing. I have a t-shirt. I'm also trying to make a mug, a coffee mug. You'll see. It's fine. Maybe that will happen. If it does happen, I'll let you know if that's actually happening. Okay. Okay, see you next month. Thank you again for your support this month. I will see you in April.